Next speaker is Professor Jiro Soda. Are you around?
Yes.
Okay.
Can you hear me?
Yes, I can hear you. You have 25 minutes. Please go ahead.
Yes. First of all, I'd like to thank organizers for giving me this opportunity to talk about Magnon limits on high-frequency gravitational waves. This talk is based on the collaboration with Ikeda, Ito, and Miuchi. Two of them are experimentalists. I'm not experimentalist, so maybe if you ask me the details of the experiment, I'm not sure, but I'd like to explain our idea to detect the high frequency gravitational waves. So basic philosophy of our work is the following. There exists duality of action and gravitational observations. Actually, detectors useful for action search is also useful for gravitational wave search. And opposite is also true. Detectors useful for action search is also useful for gravitational wave search. For example, gravitational wave interferometers can be used for probing the action, ultralight actions. And similarly, using pulsar timing arrays, we can probe the ultralight actions as first pointed out by Rubakov and his collaborators. Today, I'd like to explain how to use Magnon to detect the action. And I'll explain how to use Magnon to explore the high frequency gravitational wave. This is a main topic of this of my talk today. So first, I would like to explain probing the action with how to probe the action with Magnon. This talk is based on the foreign paper. So let me start with the very basic of the condensed matter physics. So first, I will consider two electron system. This is a kinetic term for two electrons, and we consider the Coulomb potential. So as you know, the electron has the spin. So there is two parts of the wave function. In configuration space, we have we can classify the wave function into two parts. Symmetric part here, this is a wave function for a single electron. So if you exchange position of the electrons, this wave function is symmetric. But we can also construct a symmetric wave function like this. And about the spin state, we can classify the spin state into the triplet state and singlet state. Since the electron has Fermi status, we have to combine these wave function into the singlet wave function, the triplet wave function, which produces a minus sign when we exchange the two positions. That reflects this symmetry of Fermi status. So given these two wave functions, we can calculate the eigenvalue of the Hamiltonian. And for singlet state, we have this formula, and for the triplet, we have this. Here, V is the Coulomb integral, and U is the exchange integral. And I is overlapping integral, which is used for the normalization. Here we have E0, which is constant, but it's not important. Because of this exchange integral, we have two signs. So, but if you use the following operator, you can combine these eigenvalues. So S1 and S2 is a spin, just spin operator for two different electrons. So eigenvalue for the singlet state, we have this eigenvalue. Okay. So for the triplet, we have eigenvalue 1/4. So because of this relation, we can combine these two eigenvalues into this form. So the Hamiltonian becomes in this form for two electron system with coupling constant here. And we can easily generalize this consideration to general n electron system, which is a Heisenberg model. So we have we can understand the interaction between spin in this way. Okay. Next, we consider the interaction between electron and electromagnetic fields. Here we have the Dirac equation in the presence of the electromagnetic field. If you take the wave function, if you decompose this wave function into electron and positron, then you can write down the Dirac equation in this way. Then you can eliminate wave function of positron by just substituting this here, this into here. Then you can use non-relativistic approximation. You can expand the result by 1/n. That means the mass of the electron. Then at the lowest, you can get this Hamiltonian. If you use the simple formula for the Pauli matrix, you will get this Hamiltonian. This is just a conventional kinetic term. And this is a famous Pauli term. So this describes the interaction between spin and magnetic fields. Here mu b is the Bohr magneton, okay, and S is a spin operator. So now we know the interaction between the magnetic field and spin. So we can understand the ground state for the uniform magnetic field. This you see that because of this term, so spin state, spin is all of spins are aligned in the z direction. Z direction is the direction of the magnetic field. Then usually microwaves are used for generating spin waves. Actually, a microwave has a time-dependent magnetic field. So if the direction of this time-dependent magnetic field is perpendicular to the imposed uniform magnetic field, then you will see the spin waves are generated here like this. Okay. Then we can quantize these spin waves. So the resultant excitation is so-called Magnon. Let's see the Heisenberg model. If you decompose this inner product into this form, then the algebra S process must satisfy this algebra. As we saw, the ground state is this state. All of the spins are aligned to the z direction. Then in that case, we can use Holstein-Primakov transformation. Here, she and Shidaga satisfies the conventional algebra for the annihilation and creation operators. So this Shidaga C is the number operator. So if we increase this number, then the z component of spin decreases. So this describes the change of this spin of the z component of this spin. So this is similar to this precession motion. So the other component S plus S minus can be constructed to satisfy this algebra. In general, in the condensed matter, the occupation number of the excitation is much less than the spin eigenvalue. So you can approximately write down the Hamiltonian in this way. Here is again the irrelevant constant part. And you see that the Hamiltonian is not diagonal. Here, ij is the site position of the spin. Okay. Then to diagonalize this Hamiltonian, we use Magnon basis. Here, k is some wave number vector. Here, n is the number of the electrons, which is usually very huge number. Then if you substitute this expression into here, you will get the diagonalized Hamiltonian. So the Shidagasi is the number operator, which counts the number of magnons. And you can get the energy spectrum for the magnon like this. So here, delta is a vector connecting nearest lattice point. So if you consider the small wave number, this is just this energy is proportional to just k squared. Okay. As I said, usually this magnon is excited by the microwave, but instead of microwave, we can use action, because action is coherently oscillating with this quadratic potential. So in that case, the energy density is given by this formula, so which is almost constant. But pressure is given by this. Here we have minus sign. So because of this, we have the oscillating pressure here. But mass of the action is typically much larger than 10 to the minus 20 electron volt. And compared to this, Hubble scale is 10 to the minus 33 electron volt. So on cosmological time scale, the pressure vanishes on average. Thus, the action can behave as a dark matter. So if the action is dark matter, this gives rise to the oscillating scalar field. And let's consider the interaction between the action and the electron. Because the action has the shift symmetry, the coupling form is restricted to in this way. We have the derivative coupling here. So again, we have considered the electron part and the positron part for this Dirac field. Then you can get the Dirac equation. Then by eliminating this positron wave function, then you will get this formula at the leading order. This part is the same as before. New one is here. You see that the action field comes in here, and the interaction form is quite similar to the Pauli term. So you can say that this part is effective magnetic field. So yeah, in a sense, the action induces the effective magnetic field in the electron system. And as I said, the action is oscillating in time. Then this means that we have the induced time-dependent induced magnetic field. So the action can play the same role as the microwave. So let's consider the interaction part, this part. We impose the constant uniform magnetic field in the z direction, and assume the direction the action induced magnetic field is directed to this direction, and the angle between this b uniform magnetic field and this induced magnetic field is just theta. Theta is here. And this oscillation time scale is determined by the mass of the action. For example, in case of the microelectron volt action, we have the gigahertz frequency. So using this formula, we can rewrite this part in this way. Here we have the constant Hamiltonian, and this is time-dependent part. Here, to write this Hamiltonian, we use the rotation wave approximation. Now, we can use Holstein-Primakov transformation for the one of two eigenvalue. Then we have spin operator in terms of the annihilation creation operator here. And using the Magnon basis, we can rewrite the Hamiltonian. In the process, we use this calculation. We have to calculate the CI. I is the location of the site. And the summation goes like this. Here we have the normalization square root n, and we just rewrite this way. Then use this part becomes Kronecker delta. So finally, we get this relation. The important point is that we have the enhancement factor here, square root n, and here we have cartoon for the system. This is the ferrimagnetic crystal. Usually we use YIG, yttrium iron garnet sphere for the ferrimagnetic crystal. In this case, the number of electrons is just about 10 to the 22. So this gives rise to about 10 to the 11, which is a very huge number. And the system Hamiltonian becomes the force. Here H omega is just the Raman frequency. And this, here is effective coupling constant, which include Bohr magneton and effective magnetic fields. And here we have the enhancement factor. And because of this time-dependent interaction part, we get this some oscillation of this state. Its probability, transition probability is given by this formula. So anyway, we understand oscillating action field can excite the Magnon. So Magnon field, the amplitude of the oscillation is given by the energy density of the dark matter, which is typically 0.45 GeV per centimeter cubic. And the typical velocity is here. In this case, we have the effective magnetic fields is about 10 to the minus 8 times coupling constant of between the action and the electron. Now you can count the number of Magnon generated by the action. Then from that, you can read off the magnetic field. From this experiment data, we can constrain this magnetic field. So this magnetic field must be less than 10 to the minus 14 Tesla. So this gives rise to the constraint on this coupling constant, which is, so G coupling constant must be less than 10 to the minus 6. This is our result. Here we use to read out the number of the Magnon, we use qubit system. Then at this mass scale, we have this constraint, which is not so good compared to the quarks data. We are not sure why this difference appears, the huge difference appears. Okay, let me move on to the gravitational research with Magnon. This part is based on these two papers. So the time-dependent action could generate the Magnon. Similarly, we insist that time-dependent gravitational wave can also generate Magnon. So if you count the number of Magnon, then you can constrain the amplitude of the gravitational waves, which is ideal. In the transfer traces gauge, the metric can be written as follows. And the gravitational wave consists of the plus mode and cross mode. If we assume the direction of propagation is as follows, so theta is just the angle between the magnetic field and the direction of the propagation. Then you can write down the polarization tensor this way. And in the Heisenberg model, here you can see that here the metric comes in. So there appears the interaction between the gravitational wave and spin. And we assume the wavelength of the gravitational wave is sufficiently large compared to the system size. This sphere has a diameter of 0.5 millimeter.
4 minutes.
Okay, thank you. So in this case, we obtain the effective coupling constant. This part is similar to the action case. Here we have extra coupling constant coming from the gravitational waves. So if we constrain this G effective, then you can constrain the amplitude of the gravitational wave. So we haven't done any experiment, just borrowed the data from the quarks and Flower et al. 2000. This data tells us that G effective is less than these values. So we can translate this constraint into the constraint on the strain, gravitational wave strain. The result is as follows. Because this experiment is done at this frequency, so we have the constraint on the 14 gigahertz gravitational waves, whose strain must be less than 10 to the minus 22. And similarly, at 8 gigahertz, we have a constraint by this value. Okay. However, we must be careful about the coordinate system because of the equivalence principle. So we have to start with the Dirac equation, and we have to use proper frame coordinate system. Then this A is the acceleration of the detector, and the omega is the rotation of the detector. And this we can see the Riemann tensor. Using this proper frame coordinate system, we can calculate the effective Hamiltonian in the using the non-relativistic approximation. Then we got these complicated results. Here you can see that there arises the interaction between the gravitational wave and the spin. But in this case, we have this derivative. So in order to obtain the effective coupling, we have to take average in this part. Then after the averaging, we get this separation factor. Here, L is the system size, say the 0.5 millimeter, and lambda is the wavelength of the gravitational wave. So in our case, this gives rise to the about the 10 to the minus 3. So taking into account account this separation factor, we get this new constraint. And we get the some constraint on the gravitational waves, gigahertz gravitational waves. So let me summarize my talk. Action, as I said, action and gravitational wave observations have a kind of duality. So it's well known that Magnon is useful for action search. So our idea was that from the duality, Magnon should be useful for gravitational wave search. Utilizing the available data of action search, we have given Magnon limits on gigahertz gravitational waves. Of course, this data is specific to the action search. So if we develop a detector specific to gravitational waves, we can expect more sensitivity and extend observable frequency ranges. Thank you very much.
Thank you. Is there any question for Jiro?
Could I ask,
Yep.
as far as I understand it, the sensitivity is related to the size of the YIG crystal, and that was something like 0.5 millimeter. Is there a possibility of having bigger crystals?
All right. Well, what's going on? Oh. Yes, this size is 0.5 millimeter. I asked the experimentalist, is it possible to enlarge this size? But they said it's difficult. So they said it's not impossible to enlarge this size to, for example, 10 times.
Okay.
But it's difficult more.
Thank you.
There is another question by Michael Tobar.
Yeah, I think what the Quarks guys are doing is they're using more than one sphere to get an effective, bigger system.
Really?
So, yeah, they've worked out how to do it. Yeah, we did some limits on without, but we put some limits with one sphere, but we've got that on the back burner until the axion is detected. Then the Magnon will be able to tell.
What size? What is the size of the?
Well, we have a 5 millimeter sphere, and I know quarks are using 1 millimeter and putting 5 in one detector, and they've got a way that they can hybridize together to make an effective detector of bigger size.
So they increase just number of the YIG?
Yes, number of Higgs spheres. They've got a way of putting them in the cavity, so
that's a good idea.
Okay, more questions? Okay, I don't see any more questions. Thank you very much. And now the